Okay, good morning. Well, good afternoon, actually. It's January 1st, so I'm going to go ahead and get right into the next lesson. So this is a continuation onto the concept of lift, and in the last video, we had the four forces of flight, which we discussed, and of course, there was a video, and if you can't remember, or if you're catching this video from another area, basically how it went is you'd have the airplane right there, and then we'd have our lift vectors. So we'd have our lift right there, weight right there, drag in this direction and thrust in that direction. Okay, so this is what we discussed last time. That's your four forces of flight. So what we'll be discussing this time is we will start getting into the lift component right here and go in more into detail with that. Well, before we can even start talking about lift, you want to talk about the theories of lift, or the theory of lift, if you will. And that's the interesting theory. That's the interesting thing about lift. It's actually a theory. It's not a fact, or it's not the law of lift, or it's not the fact of lift, or it's not the general, consensus. It's actually a theory. Even to this day, NASA still runs studies about how lift affects an airfoil, or how lift operates, or how the concept of lift comes about. Because as aircraft go higher and they get faster, and we keep pushing the boundaries, we find out that weird things start to happen, especially when you start going to supersonic flow, which is faster than the speed of sound. So to keep things simple, though, we'll start breaking it down into the lift component, or the lift vector. Okay, so what we'll talk about is the Newton's three laws. Okay, Sir Isaac Newton. And if you don't know who Sir Isaac Newton is, then well, you should, because if you're old enough to be seeing this video, then you pretty much should have been old enough to go to science class. And if they didn't teach you that in science class, then I weep for our education system. But anyway, Newton's laws of motion is basically what we use to govern forces interacting with each other. There's three laws, one, two, three. So I'll go into them in detail. So the first one is that every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. Basically, in layman's terms, that is, an object at rest will remain at rest until acted on by an outside force. A lot of times when they study that, what we'll use a pool ball, or the cue ball example, on a pool table. So you'll take a pool ball, if you will. Let me see if I got one right here. Okay. All right, good. So you got a ball right here sitting on a table. This object, unless an outside force acts on it, will not move from this area. And usually the example that we use is another pool ball hitting it. So let's say we had another cue ball right there, and it moved directions and it hit this one. Well, this cue ball will move in proportion to the force exerted on it from this one. But that's essentially what it's saying. So in layman's terms, this cue ball will not move until this one hits it. The pool example. Of course, though, it doesn't have to be another cue ball hitting it. It can be a multitude of other things. It can be gravity, for example. Let's say a cue ball. Let's say I'm holding it, right? So let's say, okay, here we go. I'm going to try this. So let's say I'm holding it. As soon as I let go, it's going to fall. Well, what's acting on it to make it fall? Well, gravity is, and gravity is exerting on it. If there wasn't gravity, then it would just be sitting there stationary, unmoving. So there has to be an outside force working on the object to make it move, and that's the concept behind that. It gets a lot more complicated from there, but for the very beginning aspect, or as far as like flight training is concerned, all you want to be concerned about is that an object at rest will stay at rest unless acted on by an outside object. Okay, so let's continue. Hopefully I didn't thoroughly confuse you on that one. Now your next one that you have is force is equal to change of momentum per change of time. For a constant mass, force equals mass times acceleration. F equals m times a. So in layman's terms, it's force equals mass times acceleration. So we'll put that down right there. Force equals mass times acceleration. Okay, and hopefully you can see that. I know I'm just drawing on crayons here, but it's a very it's a very off the cuff lesson, so it's not very formal. It's not like you're paying for it. Well, unless you do donate, so then you aren't paying for it, and that's why I'm here. So, okay. Force equals mass times acceleration. This is actually important in flying, and people do not explain this nowhere near in detail like they should. Um, the force, of course, is how hard an object is going to hit another object, how much it exerts. The key component here, though, is your mass times your acceleration. And what people get confused about, especially in Earth terms, did I just say Earth terms? Well, especially in terms that we know of, is people construe mass to weight. And weight equals to force, which you would think would make sense. Like a 4,000-pound truck, you think is going to hit harder than a 2,000-pound truck, or a 2,000-pound truck won't hit as hard as a 4,000-pound truck. But what's important to remember is the force that is exerted on an object, or an object exerts, is entirely dependent on its mass. And its mass is the displacement of an object, exactly how big it is. It has absolutely no bearing on its weight. Now, the problem is that there's really no easy way to correlate weight with mass. But the reason this becomes important is when you start moving in environments of low gravity or no gravity, if you will. This is a very big concern, like on the space station, because you can't take, like, let's say this cup, which is very lightweight, like what it would be on the space station. You could just move it around with your fingers or whatever. You just can't go flinging it down the hallway, because what it's going to do is it's going to impact an object with the same amount of force that you would as if I had flung it on Earth, because the force that exerts is dependent on its mass, which is actually how big it is, not dependent on its weight. If you need another lesson about this, I know if you watch YouTube, you always see those YouTube videos where somebody's getting taken out by those yoga balls, like those big old inflatable yoga balls. And if you don't, just go to YouTube and donate or donate. Go and Google or go on to YouTube and look at yoga ball ownage videos. And what you'll do is you'll see people taking those big inflatable balls and basically knocking people out with them, because they think, well, it's a big light ball, or it's a big ball, but it's full of air and it's light, so it's not going to put a lot of force to it. But what winds up happening is they throw it, and since it has a lot of mass, it exerts a lot of force, and then that's why the people go flying back or down the stairs or whatever. So this is very important on landing too. This is why you need to keep your speed under control on landing. A lot of it is this right here, but this doesn't, I think, get explained in detail like it should. So force equals mass times acceleration. Okay, and I got 2 minutes left. So last one. For every action, there is an equal and opposite reaction. That's pretty self-evident. Basically, that's how jet engines work. That's how any type of propulsion works. It pushes stuff out the back. The resultant force pushes you forward. You got, for every action, there's an equal and opposite reaction. Okay, well, that's about my time. So that was the introduction to Newton's 3 laws of motion. If you have any questions, let me know, and we'll continue on in the next set of videos.